Yesterday. Oh, look in the top drawer of your tower. I don't know if we went over this or not. Look in the top drawer of your tower. I've gotten lazy on you.
No, you didn't get lazy. You got
Smart. Something like that. Okay, so take that out. I've already typed in a number for this week, but I will gladly increase the number if you get higher than 5. Yesterday, we started our probability chapter. And as you can tell, probability, some people would say, is kind of intuitive. So eventually there are going to be some formulas, but I really think you can BS your way with probability. It's just my opinion.
Constance?
Yes, ma'am.
I'm sorry to interrupt. Was Caitlin Pertower in your third period class today?
Yes, ma'am.
She was.
Yes, ma'am.
Thank you.
Okay. So let's talk about probability. So the only issue I have with this chapter is it doesn't really seem tied to anything else we've done. Like, it's just been kind of random. Like, first chapter was about basics of stats, how to do one variable stuff, how to make a graph. Chapter 2 was on the normal distribution and how to deal with that. Chapter 3 was linear regression. And you're like, okay, linear regression was 2 variables, so I guess that makes sense. And then chapter 4 was like how to do sampling and how to make an experiment, which I guess makes sense because we're talking about how to interpret the results, so I guess I can see it. And then here comes chapter 5 out of nowhere with let's compute some probability. It is. So by the end of it all, it'll all, tie together. But for now, it's just like, this doesn't really seem like anything else we've been doing. Yes, dear.
I left my coat, Mr. Brown's name.
Yeah.
You left your what?
His coat.
Oh, they say
Okay. So probability is the mathematics of chance. And the big idea is that, we can't predict chance behavior. Like, we can't predict exactly how the coin will flip if we flip it. But there is eventually a predictable pattern in the long run. So we're supposed to think, there are thinking exercises. We're supposed to think about the following situations. Situation 1, tossing a coin 5 times and getting 4 or more heads. Does that seem very possible?
No.
No, it seems like the odds of that would be very small. But does it seem like if you toss the coin 50 times, you get 40 or more heads? Does that seem like a higher percentage or a lower percentage?
Probably common.
I don't know.
I would assume.
I would say low.
So-
Basically the same.
Well, and then obviously it's the question that we're both asking, or we're all asking in our heads, which situation is most likely to occur? Or do both situations have the same probability of occurring? Because she's saying 4 out of 5 and 40 out of 5 or 40 out of 50 reduced to the same thing.
I can see either side, honestly.
And then, so write down your thoughts and your reasoning. So we're clearly going to eventually get to the point of this. It's just to get you interested. I can see her argument, but I can also see the argument of I threw it just a couple times. Maybe there was odds that 4 out of 5 I did. I threw it a bunch of times. Seems very unlikely that this pattern would keep happening.
Weighted on one side or the other.
Yes, something would have gone on. It's in my top right drawer. So the next thing is the law of large numbers. And as we observe yes, perfect, you're so smart. As we observe more and more repetitions of any chance process, the proportion of times the specific outcome occurs approaches a single value, which we call the probability of that outcome. For example, because that just sounds crazy. So basically, the more and more we repeat something, we tend to approach like a certain value. And you would guess, if we flipped a coin more and more times, what probability, what percentage do you think we would have come here? I would guess 50%, because there's 2 odds. Yes, dear?
Would it affect it at all? There's like, how you get coins that are just at the bottom of your bag or whatever, and they just get gross and get stuff on them? Would that affect the probability of it?
Absolutely. Because one could argue that was weighted, or one could argue there are some lurking variables there. Yeah. Okay, so, and then, of course, they steal my example. Man, they always steal the coin. Who doesn't want to, though? As we toss a fair coin, so Kenzie's coin wouldn't be fair, over and over, the proportion of times that it will land on heads will approach, we would assume, 50%. That makes sense. And if we toss it 1,000 times, we expect it to be 500 out of 1,000, because 500 out of 1,000 is 50%. And will it be exactly 500? Probably not. It might be 498, it might be 502, but the chances that it deviates significantly from this proportion would be incredibly rare. So the chances of it being 400 out of 500 would be very, very rare, and you need to question whoever's flipping said coin. Okay, and then here's some common sense stuff, but we gotta say it just in case. Yes, dear.
The fraction says 500 out of 10,000.
It does. We need to get, thank you. You can have a point for that. Too bad it's a PDF and I can't fix it. I didn't notice it, did you? Okay, and then so we're going to say the obvious, which I think you already knew because you understand probability is normally interpreted as a percentage. So a percentage is normally between 0 and 100%. So if we're doing it with decimals, we're meaning between 0 and 1. So probably any outcome is a number between 0 and 1. There are things that are outcomes that never could occur. You know, we joke that pigs don't fly, but like something like that, the probability of that happening is about 0%. And an outcome that always happens has a probability of 1. And the mathematics of probability is based on imagining what would happen in an indefinitely long series of trials. Okay, and then this is kind of back to last chapter. I guess there is a little bit of overlap. We can use a simulation. It's kind of like an experiment where we're just, basically a simulation is an experiment. So where, for example, rather than having 100 children find an estimate for the true probability of having a girl, we could put 2 names in a hat, draw and replace a card 100 times, and record our results. Oftentimes, we can use technology such as a computer applet or a calculator to simulate this chance probability.
How old is this?
Applet.
Well, how old is this? Yeah.
Oh, no, actually it's new this year.
So, what if the probability
Is
of
it
getting like
Applet?
50%, would it be
Or-
closer to like 50% with a calculator or with the hat?
We would hope they're all about the same. But basically, that simulation chapter goes into, if we're questioning something, we could run our own experiment, because we would want to do it. We talked a lot about doing things with a hat, a lot about doing things with our calculator. But there are specific programs on the computer that deal great with probability, even though you hate the phrase applet. There are computer-based programs that deal well with probability and actually show cool simulations. So I'm going to eventually stop rambling. Eventually, I'm going to stop rambling. Why? Because I can't speak. And we'll see if I can make I haven't used it forever, but we'll see if we can make it go. And I can show you how my computer can do a coin thing, and a hat thing, and a couple other things that I just can ignore. It's not really that cool, but better than nothing.
That's astonishing.
You just want to not do math.
That's cooler than the computer I don't have.
Okay, clearly Miss Compton cannot read. Did someone go ahead, Kenzie?
At a local high school.
Your name is not Kenzie. Kenzie, you can have a point for him being a jerk too. So go ahead, Kenzie.
At a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden student parking lottery at a school center. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member from the AP Stats class. When those golden tickets went to members of that same class, some people thought the lottery had been rigged. There are 28 students in the AP Stats class, all of whom are eligible to park on campus. Design and carry out a simulation with 30 trials to decide whether it's plausible that the lottery was carried out fairly using Table D. Discuss your method evaluation. That's all really got.
Yeah. Discussing. So table D is actually in your textbook, the random digits table. So I'll give 1 to each table. Okay, so how many spots are there, or what do they say?
There's 2 tickets. Wait,
There's
never
2
mind.
tickets. How often?
2 lucky winners.
2 lucky winners. How often?
Last of
Each
the
one.
drawn.
Okay, and how many are in this AP Stats class?
28.
Okay, and they were both both chosen. Oh Lord, they were both chosen from the AP Stats. I know, it was great. They were both picking. It says 28 students, all of whom were eligible, and it says some people thought the lottery had been rigged.
So does every 2 out of 28 students? I don't understand.
Okay, so, but how many students were there possible, total?
95.
So there were 95, and we randomly picked 2, and both the people we picked were in here. And what are the, well, obviously not even in here, it's double our size.
Got
And
it.
what are the odds of that?
Got it.
Probably extremely small.
So, you know, it's like,
That student is so large
But
compared to
because
the 95 students.
it's a pretty, 95 students is not as big as.
So, there are 28 of them out of the total 95, so that's over a fourth. So I can see the first, like 25% chance of the first one,
But it's two of them.
but it's 2 of them. So we want to figure out whether or not it's plausible
So it's like a
using our random digit table. So you and I already know that we're going to look for how many digits on the random digit table. Yes, because we're going up to 95. So we're looking from 0, 1 to 95. We've assigned every student a number. Maybe Alex is 0, 7. We don't know. So we're looking, and we're randomly going to pick 2. And we're going to say specifically 0, 1 through 2, 8 are the AP kids. So if it just so happens that the first 2 numbers we see on the random digit table is between 0, 1 and 2, 8, then yeah, it's possible. But what if not? Okay, so we're looking at our random digits table. Where's that?
How would they do it though?
Well, but it is, I mean, they are the ones who chose it. People are always going to say stuff. So we got to prove we didn't.
After getting the 2 digits, do we go continue down that row or go to the next row?
I'm going to start at 101 and stay there.
Okay.
So I'm starting at my random digit table at line 101. And at line 101, the first random sample chosen is what number? 19.
Can I just point something out?
Yes, Dan.
It says that the tickets were drawn by a member from the AP.
And that's why people are having a problem with it.
Yeah, I can see that. I'd be
Okay. So it was 19 is the first person chosen. And when we chose number 19, is number 19 in the AP Stats class?
Yep.
Yes. And then what's the second number we chose? Is lucky number 22 also in the Stats class?
Yep.
Yes. So, I don't know, but this seems crazy. So let's do it again, but let's do a different line. Let's do line 102. So line 102, the first student we pick is
19.
Isn't it 73?
Oh wait, we're doing it out of 95.
Yeah, so I agree that, no, I was with you there for a second. I had gone halfway down the line before Jana brought me back to Earth. So 73, and the second person chosen is?
67.
Okay, so when we chose from line 101, both were in stats. But when we chose from line 102, neither were in AP stats. So let's try line 103 just for fun, and then we'll call it a day.
Wait, we're not actually supposed to like find the actual like
Well, I mean,
possibility of that happening.
we are going to, yeah. I just can't resist, but know that the problem say we had to, or did it just say set up a simulation with 30 trials?
That's a lot of trials.
Yeah, we're only going to do 3. That's all Ms. Bum has patience for.
Sure.
10,
So 103 is, what are my 2 people?
45, and 46.
What about 45 and 46? Are they both in it?
Nope.
So it's not looking good, is it? But again, Miss Compton is ignoring directions because I've only done 3 trials and it said to do how many? 30. It said to do 30. So we'll come back to this because Louise wants to know how to actually do it probability-wise. We're going to come back to that. But let's go down to the bottom. It says, well, I mean, that's what we should want to know. It's this probability checker. It says, can we do it? Use the random numbers in your calculator. So one person in your group, let's do it. Let's say we're not doing 30. Let's say we do 15. 15 times.
Got the boys.
Then looking down the line, so far the next AP stats class kid happens in line 114.
But it's fine with me if you just, like, maybe Alex does 5 of them and Mackenzie does 5 and Sally does 5. They're just your 15. Yes, only 15.
How many numbers?
We need 2 numbers for each, right?
Aren't we doing 30?
We're only going to do 15.
Are we doing 15 numbers total, or are we doing 15 so each draw is?
We're doing 15 trials, so you're going to need 30 numbers.
Oh, so that all the numbers up here.
Here's the rainfall there.
Or wait, would you do 1,95, 30, or 15?
Well, we're wanting 2 free, so it's 30.
Oh.
You gotta split it.
And I might want to send it, because I'm wanting so many, I might want to send it to L1 or L2 to one of my lists.
Are we reseating the calculators?
We're not going to reseed, we're just going to pray that life's normal.
So it ought to be 1,95, 2.
Comma 30. Well, I mean, if you're willing to do it one at a time, sure, but we're going to just go ahead and knock out all 30 bad boys.
What?
We're doing 15 trials, but we need 2 numbers for each trial, so might as well go ahead and get all the numbers. We need 30 numbers total.
Oh, okay.
Senor. Senor, Frank.
Um, 95, 30.
Yeah.
So 12, 5.
I don't know, we gotta
But that's fine, because unless it's back to back.
just back to back.
Like, not, it's like I have, okay, it just depends on which trial you're breaking it up as. Like, if I have 49 again, it's fine, because it's with number 3.
No, they're gonna be together.
Then ignore it, and you're going to need to do one more random.
Okay,
But I think you already knew that, didn't you?
I was guess. Oh no, I hate this calculator.
Alright, my master plan, that's worked. I've destroyed your operating system.
No, you didn't. It's just not letting me scroll.
It's broken.
I hate it.
I foiled you. I'm an expert foiler. First, outer, inner, last. Foil.
Bless you.
Thank you.
600. 487.
There is my calculator doesn't want to let me scroll at all.
Then why didn't you press stow and store it in one of the L's? That's what I did. I pressed stow and I stored it in like L4.
So
Stow it somewhere.
Someone's describing. Those are the memories.
Okay, does everyone have all their numbers listed? You have all your pairs. Okay, then I'm putting a star by mine. That would actually be double in AP stats. So if you have any 1 through 28, like I have 1 and 11, those are both below 28. I'm putting a star by it because those would both be kids from AP stats. And my proportion was 2 out of 15, and I want to know yours.
You only have one that's both stats.
You only have 1, so table 2 has a 1 out of 15.
But there are other ones
1.
that are just one that's stats.
Yeah, but no, we're wanting to know both.
Okay. I just want to underline all the ones that are.
So we're not actually gonna find like the actual like probability of happening.
Okay, so why are these people fighting about a parking spot? It's really not that.
I want a parking spot, dude.
I don't know.
Like,
I would just have their spots.
I guess because of the third sentence. Reserve parking spots next to the school's main entrance.
Like, I would
there's only
complain about.
90-something of them that can drive, so they can't be that far away.
I don't know. We'll work on that in a second. Table 1 or 3, how many out of the 15 were both in AP stats?
I'm still kind of
1.
You got 1.
Yes.
Hunter, if you get different, tell me. We'll make a list for you too.
Okay.
What about y'all, Ashley? How many out of the 15 were both in AP stats? We don't. Okay. Hunter, you got your thing?
Not yet.
Okay, well,
Give me so many repeats.
okay. Samantha, do you have something different?
Yeah, I didn't have any.
You don't have any. 0 out of 15. I like it. Have y'all figured it out, Jared? 3. Interesting.
I had 15 out of 15.
That's the kind of thing we want to hear right there. Let me tell you.
Yeah, that is probably at least a little bit.
Okay, so back to the while Hunter's figuring out his final decision in life. Back to the thing at the very beginning, the 4 out of 5 versus 40 out of 50. Clearly, when we did fewer trials, we had a 1 in 3. Whereas now that we're doing a lot of trials, 2 out of 15, 1 out of 15, 0 out of 15, like it's getting smaller. So the more trials you do, the closer we're getting to the true probability of it all. Yes, dear?
I got 1.
Okay. So we could, if we had the patience or the need, we could make us a cute little dot plot going from 0 to 15. And we could see, where are most of the data sitting. And we've got 2 1s, a 3, my 2, and a 0. Oh, and we got a third 1. So it's looking like the more we do it, it's supposed to be closer to a 1 out of 15. So what percentage is that?
13.
1 divided by 15 times 100.
I'm going to say
6.7%.
Yeah, so yay, calculator. So we say it's about 6.7%. It was 0.667, so they said 6.7%. So we're assuming the true probability is really close to 6.7%, whereas that 1 divided by 3 was a 33%. So that was way too high. So it's probably a good thing we increased the number of trials. And I'm betting if something wasn't restricting you to only the 15, if we did the full out 30, we get to even closer to the real truth. Okay, but again, this is how we would attempt to find the truth. Louise wants to know how the actual probability would go. He wants to go straight to the punch and for the jugular. Why, I don't know. So, I do know. So there were 28 out of 95 for the first selection. And then for the second selection, there were 94 people and 27 stat students available. And if we multiply those together, so 28 times 27, we get 756. 95 times 94, we get 8930. So 756 divided by 8930.
8%.
We actually get, so the actual real truth was 0.0846. So that's about 8.5%.
Yes.
So our 6.7 was not really the truth, but it was way closer to the truth than that 33. And so did they actually define the truth? No, you and I were just going to go ahead and unveil it and pull off the Band-Aid, so for the fun. Might as well. Are there any questions about this?
No.
So again, the more trials we do, the closer we would get to that number. We were just lazy. We weren't that far away. Okay, flip to the next page. It says the sample space is a set of a chance process is a set of all possible outcomes. So if we had a die, what would our sample space be?
6.
Because there are 6 sides. We assume if it's a normal standard die. It might be something fancy. We don't know. And then a probability model is a description of some chance processes that consist of 2 parts. You've got to have a sample space, and you've got to have a probability for each outcome. So if our sample space were the 6 sides of the die, then the probability outcome for each, if it's a regular old non-weighted die, would be what?
1
I'm
6.
assuming
Yeah, because there's 1 in 6, because there are 6 sides.
Doesn't make sense.
Same way with if it was a coin, we'd say there were 2 in our sample space, heads or tails, and me 1/2. I'm telling you, probability is kind of, well, until they start doing that weird stuff we were doing yesterday, like this given that, until they go weird on you, it makes perfect sense.
I like probability.
An event It's a collection of outcomes for some chance process. That is, an event, you know that happened because I was completely 100% caught up on my grading besides the back of y'all's tests.
What?
That person brought in another paper. I jinxed it earlier. I was like, yay, I don't have any papers to grade.
Oh, wow.
Bummer. Okay, so an event is a collection of outcomes for some chance process. That is, an event is a subset of the sample space. Events are usually designated by capital letters like A, B, C, and so on. And so if A is an event, we write its probability as P of A, which is read the probability of A, or probability of event A. So yesterday we were doing like P of, we didn't even label it like this, but like, well, they eventually did, but like P of sophomores. Sophomores.
Yes. Right?
Yeah, sophomore. Yeah.
And then so eventually we get lazy and we would just say P of S.
Smart though.
But we would do a capital S.
Wait, do you always put a little thing on the top of the capital S?
No, I was just doing mine ugly. My pen and me, and we were having a day. That's why you write in pencil. Okay, it says exercise. Create a sample list of all possible outcomes of the sum of rolling 2 fair die at the same time. Yay! So, should we draw a picture? Let's just go.
Can we just do the math?
What would the list include? How many things?
2. Wait, no.
How many things would it include?
36.
Why?
Because there's 6 sides on each die, and you have to do the math.
I don't believe him. Does anyone else not believe him?
I don't know what the question is. I'm
I
gonna trust it.
wasn't, sorry.
Well, if there's 6 possible pairings for each number.
I trust number Crandall of my life.
Well, actually, I don't know about that.
Not mine.
I don't know about that.
Yeah, I'm gonna say 36.
Because even if you did that, as soon as you do the 6 count,
It's 36. Yeah.
I don't know. I'm trying to see if the boy is right.
It's 36 because there's 1/6 chance, and you have to multiply it by the other 1/6 chance, so you get 136.
Okay, but did we actually do what it said?
What is sample? Create a sample.
Create a sample space. Did we create the sample space?
yeah, there's a sample space.
So again, it's just a list of all our options. So like we could have 1, 2.
1, 3.
Oh, let's start off at the beginning. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and then I'm gonna do the same thing with 2s,
Yeah.
and then 3s,
Wait.
and then 4s, and then 5s,
Well, no, they're
and then
not.
6.
No, because it's, yeah, they're not repeats.
They're not repeats.
Yeah, so it'd be 36.
If you count it as like an XY kind of thing, they're technically
Yes, they're technically not. So if our first die was a 6 and our second roll was a 2, we've included it. I mean, we have all the things.
It's not even technically not. They're not repeats because they're different die. Getting different
Technically, yes.
I don't like that, but I also do.
You're the one who said 36. You think you'd be happy.
I am, but I confused myself, and then I'm confused and not confused again. I'm the confusion. I am
Alex
confused.
is fired. Arkansas.
That's such a good one.
Arkansas.
Why is it Arkansas? Arkansas.
Okay, but Miss Compton technically hasn't followed directions.
We did it?
I did not.
America.
I've already written like half of these.
No, this is still right, but I'm not done. Point. It says sum, so I actually need to add all these. So it's 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8,
I'm gonna guess the answer
4,
is 100.
5, 6. You already know 6 plus 6 is 12, so why would you say that? 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11.
It's basically to do this.
Serious.
It was doing the multiple.
It's not a summation thing. I hate summation.
Oh, that would be the easiest way to
I
notate
really
it.
hate a lot of physics in it.
What?
I just really hate a lot of physics in it.
There's a lot.
Make that summation out.
I mean,
He's doing sequences in series with convergent and divergent, and he's
yeah, I don't understand what he's saying. This is like
no,
you
he's
add
in a
things.
different league with the summations. His is not.
Oh, he's talking about those different.
He has different things he has to do. It only gets worse.
Integral.
Math
I'm
wise.
confused why
Check your
now
integrals.
did it like that.
I did like 3 plus 1 is 4.
Integrals.
3 plus 2 is 5.
Did you do your best?
So my brown is me adding. Yeah, 'cause it said,
They never said
Kenzie noticed it said the word
it's
some.
fine, it's anything you do, like-
Okay, but eventually someone else is gonna know.
3, 4, 5, 6, 7, 8. I was making sense. I get it.
Okay, but eventually someone else is gonna notice something else smart. I pray they will.
Well, so, I mean,
Yes, I'm not saying that. Did we follow directions now?
Sample space, listing all possible
at the same time.
There has to be.
Okay, but
a sample space.
sample space of a chance process set of all possible outcomes. So we've listed all the possible outcomes. Yes.
So, does it have to do with at the same time?
That's what I said, but I think we already did that by putting them together.
I think so too. Okay, and now the next part, is everyone good with that? Okay, then it says create a probability model that illustrates the sample space of the sum of two dice and associated probabilities of those sums. Okay, so we're going to just say the P of rolling the sum, I'm going to put S2, sum of 2. The probability of rolling a sum of 2. We know there are 36 options, but how many times on our list do we have a 2?
One.
Just one, so it's 1 out of 36. Okay, what was our probability of rolling, I guess I should say probability of rolling a 1. And that was 0 because it's not possible. So should we list it? Probably not, but we will. So we did 1 and 2. Let's do probability of rolling a sum of 3. I see it there. I see it there. So it's twice. So that would reduce to 1 out of 18. The probability of rolling a 4. 1, 2, 3 times. Interesting. That reduces to what?
I feel like
If I wanted to leave as a fraction.
7 is the most common, I think.
Yeah, it's 1 over what?
Yeah, they just said it was 12.
Yes, it's 1 over 9. It's Alex, good point. Okay, then S5, the probability of rolling a 5.
Is 7 the most
I think it is
common
3.
one? Yes. I think it is.
It appears
The
it
one
is.
that-
Okay, but I think I wrote the number wrong for 4. Wasn't
Yeah,
4
4
3?
is 3 times, yeah.
So it was 1 out of 12. So, Samantha, you can have your point too because Miss Compton was blonde. She wrote the wrong number. Alex told me the right number.
Whoa.
Wait, what?
You were right.
4. It was, you were right. I wrote the wrong number, and then you still reduced the wrong fraction for me because you love me, Alex. That's what happened. Thank you for rolling with it. Thank you, Samantha, for catching it. Thank you, Louise, for pulling out.
So you have the
Oh, yeah, die humor.
So you have the highest chance of rolling a 7.
4, the probability of S5 is 4, so 4 out of 36, which was 1 and 9. Yeah, yes to your answer. But we're supposed to eventually figure it out. You're stealing all my fun. Probability of rolling a 6 is 1, 2, 3, 4, 5. So 5 out of 36. Probability of rolling a 7. Apparently, 1, 2, 3, 4, 5, 6. So 1 out of 6. Alex get another point. Okay, probability of rolling an 8. 9. 10.
8 is 5 out of 36.
What's 9?
Is 4 out of 36. 10 is 3 out of 36. 11.
You can have a point for noticing a pattern.
Well then. I'm sorry. I'd like to argue that there's a pattern of even intervals. If you go from the top left diagonal to the bottom right diagonal, 2, 4, 6, 8, 10, and 12. Therefore,
Does it really help us though?
No, I was mostly focused on this diagonal.
I mean,
Yeah, that's what I
even that one was
That's what
obvious.
I'm
We all saw that
Yeah.
one. The 2, 4, 6, 8, 10, and 12 one was.
The second they ask about that, I'm down. But for now, the fact that you noticed the 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1 is pretty impressive.
Yes.
So yes, it says create a probability and all associated probabilities of those sums. The highest probability was that you would roll a sum of 7. So now you know if they ask you to bet on some game or what's the sum or something, you know to bet on 7. Yay, gambling skills.
That's awesome.
Wait, what?
Thank you for that.
Repeat that?
You probably just saved all of these people in here millions of dollars.
Their games are more. Their games are a little more complicated than that. But if their game was simply just, what do you think the sum of these two die would be? It'd be best to put your money on 7.
Okay.
But yes, there's a lot with gambling that there are better, higher probabilities with certain bets. Yes.
Lucky 7. 20 years.
That's what I was thinking.
Okay, so basic rules. Okay, Louise, read the basic rules, please, because I can't read today.
Basic rules of probability. The probability of any event is between 0 and 1.
I feel like we understood that already, but okay, yes, great.
The probabilities of all outcomes when added together must sum to 1.
Okay, that makes sense. Heads, 50%, tails, 50%, that adds up to 100%. 1/6 plus 1/6 plus 1/6 with all the sides of the die, and that adds up to 6/6. So it just makes sense. Okay, yes, go ahead.
If all outcomes in the sample space are equally likely, the probability that event A occurs can be found using the formula of PA equals number of outcomes corresponding to event A divided by total number of outcomes in sample space.
And that reminds me exactly of the die of if there are 6 sides, and all sides are worth the same, then it's a 1 in 6.
P of A. The probability that an event does not occur is 1 minus probability that the event does occur. This is called the complement rule.
Okay, so this is the first real new thing today, and this is the first vocab term that you really probably want to put in a box. You need to know it. So if we find the probability of tails, bless you, then it would be the same as finding 1 minus the probability of heads. Or 1, you get what I'm saying? Like heads and tails are the opposites of each other. So if you know the probability of tails, 1 minus that gives you heads. If you know the heads, 1 minus that gives you the tails. So you can always figure it out one way or the other. Go ahead, finish the last one.
Addition rule for mutually exclusive events. If 2 events have no outcomes in common, it's probability that one or the other occurs in the sum of their individual probabilities.
Okay, so this is what we were discussing yesterday, mutually exclusive. So one does not influence the other. There was, in our table yesterday, I don't remember if it was sophomores and green, or there was some, it was like freshmen and blue, I don't remember. But it was, one was 0, there was no overlap. So like freshmen do not like blue, there is no overlap with them. So if we're trying to find the probability, we literally would just sum their individual probabilities.
Neato.
And then read the last thing, because this is the coolest part about mutually exclusive.
The probability of any event between 0 and 1.
No, the thing.
2 events, A and B. You skip the thing.
Thank you.
Thing.
I know, he was being very literal, hence why I stuck my tongue out. Go ahead.
2 events, A and B, are mutually exclusive or disjoint if they have no outcomes in common, and so can never occur together. That is, if P of A and B equals 0.
And we've already seen that. Back to that table from yesterday when the overlap was 0, and they both can't happen at the same time. That's another, so I know I said complement, but another vocab term. You've got to learn mutually exclusive and also disjoint. They're synonyms. We use them interchangeably. You need to know what it means anytime you see either. Okay. And then he was skipping ahead to read the notation. So the notation of any event is, we understood the odds of any event is between 0 and 1. So the probability of the event is between 0 and 1. And that's how they might write it in an interval. Yes, well, it can be equal to 0 and it can be equal to 1, but the odds of that actually happening, very slim. Okay. Flip to the next page. I just want to read the back and then I'll stop rambling. Someone else want to read, or are we going to make Louise continue on?
I can read.
Perfect.
Literals.
Do you read little things on the left, or is that just...
I want you to just read things on the right because I don't even want
I don't wanna
to.
read.
Yeah, exactly.
The probability of the sample space equals 1 because all possible outcomes are in the sample space. The sample space is the entire rectangle in the diagram.
Okay, so you know in a Venn diagram, they tend to draw a rectangle and then some overlapping circles.
Oh,
And so they're
okay.
saying all the options would add up to 1. That's what they meant by that.
Okay.
But not even focusing on that part. Sample space, I like to go back to the die. We understood there was 1 and 6 for each side of the die, and if we added them all up, we would get 1. So it's kind of intuitive. So that one makes sense to me. Read the next one.
The probability of an event not happening is 1 minus the chance it does happen. We've already said that.
In which I feel like we already said, kind of with the complement rule. So the probability of tails might be 1 minus heads, because if it's heads, then tails didn't happen. So they write the little C, and what do they want the C to represent in that exponent?
The
What's the vocab term?
copulation.
Copulation.
Complement. Complement.
I said it.
Compliment. You said compilation.
No, I said it when you were.
After I've written it? Oh,
No, I
man.
promise I said it.
Okay.
Osteoporosis?
Yeah. It was bad.
What?
Okay, Sally, read the next one. I feel like we understood that one too. So read the next one. This is where life gets a little fishy for some people. Again, it made sense yesterday with the table. Once they start trying to do this notation, you're like, what does that mean? I don't know. So let's read the next thing for me, Sally.
The probability of 2 events A and B both happening. This is not the intersection of 2 circles in a Venn diagram.
Okay, so it might be, Venn diagrams where they overlap means they both happen, but we also saw that yesterday with freshmen and green where they overlap them and freshmen like green. And so if you see this symbol, this intersection symbol, it kind of reminds me of the capital letter A, and it really does stand for and. When the one that looks like you is I'm gonna let you read it, I swear. I think of it looks like a V for versus, and it means or. So we're either doing an and or an or. Go ahead for the or.
Okay, the probability of event A happening or event B happening, or both. We present in those circles and then Venn diagrams. In general, there's a formula to calculate this.
Okay, so we understood and meant they both had to happen, so they were overlapping. Like in our table yesterday, we looked for where freshmen and green overlapped. But for an or, it could be freshmen and green. It could be just freshmen. It could be just green. So it's going to be a lot bigger of a number, we assume, because it's a lot more options. And this is what you were kind of figuring out yesterday. If you're trying to figure out or, you add up the probability of one event plus the probability of the other event, and then you have to subtract out the overlap because it overlaps. Okay. Run like the wind. We'll come back to that. Monday? What day is this?
It's Friday.
It's Friday.
I don't know.
Thank goodness.
It's weird because there was a game yesterday.